All right, continuing with our development of logistic regression, we now have to deal with the issue of cost function. Let's do a recap. We have our h theta that expresses probability. We make a probability determination for a data instance x, and this value is going to be between 0 and 1. So, for instance, if we have a data set, here we have a data set with two features, and we have our determined credit risk here. And we want to use that to develop a model that has thetas, and those thetas will give us a decision boundary. So we want a good decision boundary. We need a method of determining thetas that gives us a good decision boundary. We can't just eyeball it. So as in the linear regression approach, we find a cost function that when it's minimized, gives us a good decision boundary. Now one might think, well, we want our probability to be close to the actual determination, right? If the determination is 1, we want our probability to be close to 1. If the determination is 0, then we want our probability to be close to 0. So why not just take the deviation between the actual determination and the probability, square it, and sum over all instances, and use that as a penalty. Now that's not an unreasonable way of going about it. The problem is that in practice it doesn't work. It leads to great numerical difficulties. This function of theta, which remember depends on this function h, which is quite complicated, has a very irregular shape and is not nice and bowl-shaped like the penalty function we had for linear regression. So here, for example, is a particular representation of this cost function for a two-parameter model. Now, if you want to minimize this, it would be somewhere down here. But you can see that if I wanted to use some kind of gradual gradient descent, it's going to be difficult to find this point. Right? Gradient descent is looking for a downward slope. If I'm somewhere out here, there is no downward slope. So this cost function is not a good guide towards a good set of parameters. Recall what a good cost function would be. One where if I'm anywhere in my space of parameters, I have a nice gradient that's pointing me in the right direction towards the set of parameters that's minimizing my cost function. Now it makes sense that my cost function is going to be the sum of costs from each individual data item. Now remember, for each data item, the model gives a probability, and that probability is expressed by h theta. Now if the actual label is 1, but the probability that the model gives you is 0, that should have a large cost. That means that your model is not giving you a probability that reflects reality. On the other hand, if the actual label is 0, but the model gives you a large probability of the class being 1, then that also should give a large penalty, right? So on the other hand, if the prediction is consistent with the label, we should have low cost. Now a cost function that meets all these criteria can be specified as follows. Right? We have a cost function here that is a sum of the costs from each individual data item. Actually, it's an average because we're summing over m and then dividing by m. And then the cost for each individual data item is given by this specification. Now this seems relatively arbitrary, but it turns out that there are information theoretic reasons why this is the right cost to use. This is in effect quantifying the information inaccuracy for each individual data item. So let's unpack these two conditions. Now in the case when y equal to 1, if you look at this expression, if h was equal to 1, we would have minus log of 1, which is 0, which is good, no penalty. On the other hand, if this were 0, you'd get minus log of 0, which is infinity. So if your model predicts 0 with certainty and the actual value is 1, that's giving you completely wrong information. So it's good for you to have a large penalty. Now let's look at intermediate cases. Remember that the value of h theta is between 0 and 1. So if you remember the behavior of logarithm between 0 and 1, the logarithm is increasing, the negative logarithm is decreasing. So you can see this function negative logarithm between 0 and 1 is 0 at 1 and increases towards infinity as 0. So this is what we want. Small penalty if your h is close to 1. Large penalty if it's far from 1. If we look at the other case, you're basically just exchanging 0 and 1, right? If this value is 0, then 1 minus the value is 1. If this value is 1, then 1 minus 1 is 0. So you're doing the same thing with the roles of y equals 0 and y equals 1 reversed. Explicitly, we have this function, minus log of 1 minus z, and you can see penalty is low if your value of z, or h theta, is close to 0, and penalty is high if the value is close to 1. Okay, so this is an appropriate cost function. Now it's kind of awkward to have to express the cost function in two different conditions like this. Fortunately, we can combine these two expressions into a single expression. Right here are the two expressions expressed separately as two separate conditions. And the condition is y equals 0 or y equals 1. Now actually, if we simply write this expression here, this combination of the first expression and the second expression, right? So here I've actually just taken y times the first plus 1 minus y times the second. And you can see when y equals 1, it will choose the first condition, and the second part will go away. When y equals 0, then this part will be zeroed out, and it will choose the second condition. So this sum expression here is equivalent to these two conditions here. So we have our cost function as a single function of theta, which we can use gradient descent on. This is now a function of theta which we could plot in a plane. It turns out to be bowl-shaped, and we apply the very same mathematical techniques we did with linear regression. Right, this is pointing out that if y equals 1, then the first term remains, the second term disappears, and we get our first condition here. And the same thing would be true for y equals 0. And you can see that here. Y equals 0, you have the two terms. The first term is zeroed out. The second term becomes the only term remaining. Okay? So here we have it. We have our cost function, just taking the minus out because it's common to both terms, and then we apply our minimization technique on this function. Now it looks complicated, but of course the computer is going to compute the logarithms, so as far as you're concerned, this should be perfectly fine, just as easy as it was for linear regression. Now, of course, once you get the cost function, we already have the machinery set up for making our decisions, right? You have your h, and you determine your outcome depending on the value of h. And of course, you wouldn't actually have to evaluate h. You just evaluate this theta transpose x, and you have a threshold that determines whether or not the function, the data point is determined as a 1 or a 0. Okay, we'll stop here and go on in the next video to talk about the actual minimization process for the cost function. All right, thanks for watching.